Okay, well, mechanisms. This is the last step of glycolysis where phosphoenol pyruvate becomes pyruvate and we make ATP. Notice that this reaction is named for the backward step, pyruvate kinase. That would be going from pyruvate using ATP to transfer the gamma phosphoryl group from ATP to the oxygen of pyruvate, and at the same time converting from keto form to enol form. But we're going in the other direction, and this step is irreversible. That's unusual, right? We don't usually turn a phosphoester into a phosphoanhydride and have it be downhill in energy. Nevertheless, this phosphoester is so unstable because of two things. First, the phosphoester locks the ketone in an enol form, which is less stable. And second, you've got charge repulsion between the negative charge carboxylate and then the negative charge on the phosphate group. And getting rid of both of those things, going from enol to keto form and from having the negative charges close to each other to relieving that, is what drives this reaction forward and downhill. So you've been taught to treat phosphoryl groups like carbonyl groups. That means when a nucleophile attacks, what happens? You attack the phosphate, very good, and the pi bond breaks. Good. So I'm going to just abbreviate ADP. This is the beta phosphoryl group on ADP. I'll put a little beta there. My arrow goes where? To the phosphorus. By the way, why am I ignoring the carboxylate? That's level 4, not an electrophile. Whereas this is at least a phosphoester, and we've described how it's a pretty reactive phosphoester. Okay. Second arrow needs to be what? I'll give you two options. There is the blue option or the orange option. Which is the right one? Oh, some of you got that wrong. Some of you said blue. Some of you said orange. Do you want to debate amongst yourselves? No, you just want me to tell you the right answer and get on with your lives? Too bad. Too bad. You need to figure this out. So, both of them look like they make sense. The blue looks like it makes sense more because it seems like it gets you directly to making ADP. The blue one is the correct arrow for direct substitution, but that's not how this mechanism goes. The orange arrow is the correct arrow for addition. Because phosphoryl groups are like carbonyl groups, the LUMO here is the pi star, the phosphorus oxygen pi star. If you want to break a sigma bond directly, the LUMO would have had to be the phosphorus oxygen sigma star, but it's not. Because the LUMO is the pi star, every time you add a nucleophile to a phosphorus, you're going to get the orange arrow for addition. Okay? Be careful, because I can intentionally deceive you with mechanisms that look reasonable on an exam. Please don't do that. You're evil. I am evil. But I disclose my evil tricks ahead of time. The best way to defeat a villain is to get them monologuing, which is what I do in this class, right? Okay, so then what's the correct intermediate? What's going to be bonded to phosphorus? Okay, I'm going to have 5 different, I've gotten ahead of myself, didn't I? A little bit. Well, that's awkward. How are we going to make that up? Well, everything we've done here is fine, but I believe it's too early, because I think what I showed you, Now I'm embarrassed and frustrated, but oh well. I believe what I showed you is the first thing we're going to do is basically a proton transfer step where we pick up a proton from the enzyme. And that's going to activate this phosphoester to nucleophilic attack. Is that looking more familiar? I maybe not, but that is how we talked about it in your notes a few days ago.
Why is that first?
That's first because you've got to do something. In a normal phosphoester, the leaving group is a negatively charged oxygen. And we want to do something to make it an even better leaving group so ATP can attack. So we're going to protonate it first. This protonation step that I've just showed you that comes first, proton transfer, turns what's in green to a supercharged leaving group. And I think that'll become clear when we draw what the product is. I'm only drawing a proton that got transferred to this carbon. There were two others there to begin with, but I'm only drawing the one. After we do that proton transfer reaction, notice that the oxygen attached to the phosphoryl group is now positively charged. And notice that if it left, it could leave without a negative charge on that oxygen. If it left up here, it would leave as a dianion. If it leaves now, it leaves as just a monoanion. Now, I screwed that up bad enough that I want to pause and give you a chance to catch up and ask any questions that you have about why that happens first and why that activates the phosphoester to attack. Anybody? Yeah, go ahead.
Is the reason why it's that the leaving group can be neutral?
That's right.
Allowing the phosphoryl to only attack the negative number?
Yeah, it makes it so if we did what I was originally drawing, you would imagine kicking off what's in green here as a leaving group. These electrons in the bond between phosphorus and oxygen would go onto this oxygen and it would be negatively charged. If we protonate the leaving group first, when these electrons in this bond go on to this oxygen, I'll draw the lone pair that's implied but not shown on that oxygen. When these lone pairs in this bond go onto this oxygen, in an elimination reaction, the leaving group is neutral on that oxygen. So proton transfer has turned what's in green to a super good leaving group. This is why we do it first. All right, sorry about that confusion. Go ahead.
Should we be looking for the enzyme first? Like when I'm starting, I feel like I'm always looking for like the phosphorus or the carbonyl and the double bond as my first mechanism, but should we be looking at the oxygen instead?
So in most of the mechanistic steps we've done, when a nucleophile has been attacking a phosphoryl or a carbonyl, we've done the nucleophile attacks and we've used the enzyme in the same step. It's a little bit trickier here. This is maybe the one in which we've used the enzyme first.
Okay.
Yep. And the point is, and maybe the way to remember that something needs to happen first is to remind yourself, hey, this is a phosphoester, and that's presumably level 2, so we got to do something to bump it up in reactivity in order to make it more reactive, and that proton transfer step is how you do that. All right. Any other questions about that? Proton transfer first. Once you got that, then we can do what we just suggested. That is, then we can have the resulting intermediate get attacked by ADP. And then we can generate what I call a pentavalent or pentacoordinate phosphorus intermediate. That is a phosphorus that is bonded to 5 different things. One of those is the leaving group. One of those is the negatively charged oxygen that used to be the phosphoryl oxygen. One of those is the oxygen from ADP. This is the beta phosphoryl group of ADP. One of those is an OH group, and then one of those is a negatively charged oxygen. I guess I'll keep things, there we go. So that's your 1, 2, 3, 4, 5. Phosphoryl groups, when they're attacked by nucleophiles, make a pentavalent or pentacoordinate intermediate, a phosphorus bonded to 5 things. Similarly to how carbonyls, when attacked, make a tetrahedral intermediate. And at that stage, here is the leaving group. I'm missing a positive formal charge on the oxygen. What do I want to do now to get to the products? What's the arrow? Or arrows? Elimination. So I'm going to take the lone pairs on one of the negatively charged oxygens, actually doesn't matter which, kick down, and then leaving group leaves. And that gets me to my product. Now, on my exam, you're not going to be doing this from scratch because it's multiple choice. So you can certainly draw the mechanism on paper or scratch paper. But instead, what I'll do is I'll give you a number of different mechanistic steps, and I'll ask you which one is correct or which one is not correct. You have to read the question carefully. Yeah?
Are we going to be seeing molecules that are not in glycolysis?
Are you going to be seeing molecules that are not in glycolysis? I suppose there's a chance. There's multiple ways to draw incorrect mechanistic steps. The arrows can be wrong, or the intermediates can be wrong. So sure, if you see a mechanistic step and you're like, that's not even something that's in glycolysis, that would be an indicator.
But, so you won't ask by showing something that's not in glycolysis, that which mechanisms would be
You asked, would I show you a mechanism where,
more like the mechanism sheet where it shows generic ways to
okay, you're envisioning a situation where I show you a mechanism, I show you a reaction from glycolysis, and then I give you examples from a mechanism sheet that are not even involved in glycolysis. No. I won't do that, though there's a chance when I show you, here's a reaction, which mechanistic steps are not correct. You can be incorrect because the arrows are wrong or because the intermediate's the wrong structure. Yeah?
Is the easiest way to, like, I guess, identify if it's wrong, if it's, like, attacking, like, it's not attacking the neural, identifying.
So one of the ways you can follow things is, and recognize steps that are unreasonable is, if the arrows don't indicate attack of the correct LUMO. And this was one example of that, right? We showed you an alternative where you broke the sigma bond instead of the pi bond. Well, that would require the sigma star to be the LUMO, but the pi star is the LUMO.
Otherwise, like, other than that, hard time knowing when it's, it would be easy for you to trick us and show us something that looks like, it's not.
Yeah, so the other tools for recognizing incorrect arrows, remember that arrows have to start with electrons and end either with nuclei or the space between 2 nuclei to make a bond. So one classic way to do a wrong arrow for a proton transfer, I'm just going to briefly move these. Oh, that didn't work like I wanted it to. There we go. Slide those over here. A classic way to do this wrong would be to draw the proton and do that. Like, oh, the proton goes on that carbon. Sure, if that's how we used arrows, but it's not. We use arrows for what the electrons do.
So basically, the hydrogen has to come from the carbon.
The thing that's the arrow has to go toward the hydrogen from the electrons that are doing the deprotonating. Other ways would be arrows that just don't lead to the correct next intermediate. Yeah.
Whenever there's a pi bond, well, two things. Whenever there's a pi bond, the LUMO will automatically argue the pi bond, therefore that would get passed first.
Whenever there's a carbon-oxygen pi bond or a phosphorus-oxygen pi bond, the LUMO will be the pi star.
And then looking at, so the leading group is what is the pyruvate. Is there an additional oxygen on the end, or is there only two oxygen?
Oh, holy Toledo, Batman, there is a missing oxygen. Okay, that was egregious enough. Maggie, I've already awarded them. I gave this to them, like I had to prompt them. I left it on purpose unrecorded, and then finally somebody asked. So everybody's already getting 1 extra credit point. That'll be another one for my horrible mistake. So everybody that turns in a quiz gets 2 today. Yeah. You get it, yeah. Good. All right, other questions? All right. I want you to do this one. I want you to do this one on a little bit on your own. Let me give you a hint. The first step of the reaction involves an enzyme side chain that is a thiol. And the enzyme also uses NAD+, which I'm going to remind you of the structure. You will not have to memorize the structure of NAD+. If you needed it, it would be given to you. This is the structure of NAD+. And then if you want, I'll draw you a resonance structure that really gives you a hint as to what's got to happen here. Okay, so I probably should have given you more space for this. There's space on the back too. You feel free to use what you need to use, but work on that for a minute. See how far you can go. I'm trying to figure out what kind of intermediate I should. Oh, sure. I'll give you a hint. I'll give you one intermediate along the pathway. All right, so go to it. This may take you 10 minutes. That's okay. We'll take whatever time. I'll wander around and ask questions, but just pretend for now that you're in the testing center. So I'm going to crinkle, blow my nose, crinkle wrappers, cough loudly, sniff. right. Walked around and had a chance to talk with several of you about what you were doing. Couple of ways to get started if you got stuck. One would be to look at glyceraldehyde and recognize the level 1 electrophile, the aldehyde. And then it would have been easy to forget the involvement of the sulfur if I hadn't told you this hint that you were going here and that you needed to use a sulfur. Of course, in a multiple choice exam, there'll be options so you would see the sulfur there. Let's show what happens first. A base removes a proton from the sulfur so that it can be a good nucleophile and attack the carbonyl carbon, and then you get a tetrahedral intermediate. At this stage, I'll draw just the rest of the molecule as R, and you're welcome to do this too. So this is your tetrahedral intermediate. And if you compare that to where I told you we needed to go, that intermediate isn't the same as where we needed to go. In fact, here you're at a thioester. And if you compare carefully here versus here, one of the things you might notice is the hydrogen and its electrons are gone. Where did they go? Well, then you look up at the reaction and you have NAD+, which is a hydride catcher or an oxidizing agent. So this is where NAD+ can receive the hydride that gets kicked off from the tetrahedral intermediate. You're welcome to draw this. You should be familiar or at least recognize both ways of drawing this mechanism. The two things that I've just drawn for NAD+ structure are resonance structures of each other. So you can show electrons on the oxygen kicking down, then hydride gets delivered, to this carbon, or you can draw it this way. If you draw it the way I showed you on the left, you just need one arrow. If you drew it the way I showed you on the right, you need a couple more. That kicks off the hydride. That gets you to your thioester and NADH. So we've explained the NADH, but then if you compare the product to this thioester intermediate, notice that the carbonyl carbon and the carbonyl oxygen are still there, but notice that the group attached to the carbonyl oxygen has been swapped out. And it used to be a thioester, and now it's an acyl phosphate. Again, that should sound reasonable because the thioester is level 1 reactivity, the acyl phosphate is level 1 reactivity. So what we're actually looking at here is just what we've called before nucleophilic acyl substitution. So what should my arrows do here? From the lone pair on the phosphate nucleophile to the carbonyl to get a tetrahedral intermediate. Again, what's that going to look like? It's going to look like a negatively charged a carbonyl carbon with a negatively charged oxygen. There's a sulfur leaving group here, and then the phosphate nucleophile here. This is the thing that added. This is the thing that that is going to get kicked off. And then electrons kick down and the sulfur leaving group leaves. And if you want to show it getting protonated by the enzyme as it leaves, that's fine too. All right, questions there? Yeah,
What's the rule about hydrides leaving? Like,
hydrides never leave unless there's something there to catch them.
so for some, I mean, like, what needs to be there to catch it?
NAD plus
Something that can accept electrons and
and hydrogen. Yeah, some of you were, once you got to this intermediate, or some of you, once you saw that the hydride needed to leave, some of you defaulted to the only thing you could remember about how to get rid of a hydrogen, and that was something like this. But that would be removing a hydrogen, and then the electrons there would have to have some place to go. And they don't. So pay attention. You will know you need to do a hydride leaving and being picked up by NAD plus when the name of the enzyme is dehydrogenase. Okay, other questions? Yeah.
How do you know, I guess, that there's the phenol enzyme?
If I didn't provide any intermediates, you wouldn't have known that. That's why I gave you the hint. And on an exam, you'll have various intermediates with arrows to choose from. Otherwise, that'd be a detail you'd have to memorize. Yeah. Okay. Well, I feel like that's a decent time for a break. When we come back, we'll just do the aldolase reaction, and then we'll dive into the citric acid cycle.